All this being said, the path integral is not immune to quantum weirdness. Namely, probabilities in quantum mechanics don't add like the ordinary probabilities we are used to. The reason for this is that quantum probabilities are more like waves and simple counting numbers. To see what this means, consider the difference between the height of two blocks stacked on top of each other and the height of two waves of water added together. The blocks are simple. The height of the two-block tower is just the sum of the heights of the two blocks. Waves, on the other hand, are tricky. This is because a water wave has two important quantities associated with it: its amplitude, that is, its maximum height, and its phase, that is a description of where the wave is up and where the wave is down. If two waves are in phase, then their maximum total height when added together is the sum of the two maximum heights, just like the blocks. But what if the waves are not in phase? What if, for instance, one wave is at a peak when the other is at a trough? Well, in such a case, it is possible for the maximum height of the total wave to be equal to 0, with the high points of the one wave being totally cancelled by the low points of the other. This complication rears its ugly head when trying to compute our path integral. We need to add up all the probabilities, but we need to do so keeping account of the amplitude and the phase of each wave. This is where the action comes to save the day. It turns out that the phase associated with the probability wave of any particular transition possibility is directly proportionate to the amount of action that would be needed to make such a transition. In order to determine the total probability of any quantum transition, we then only need to determine all the ways the transition could be made, calculate the action associated with each possible transition, and add together the resulting probabilities, being sure to account for the fact that quantum probabilities are waves and not just regular numbers. Indeed, it's a tall order, but thanks to the action, we have the answer that we've been looking for. Thus, quantum mechanics, despite all its unusual quirks, or should I say quarks, is not so unusual as to deny the physicist an elegant solution.